All right, energy calculations involving phase changes. Okay, so how do changes of phase affect energy flow into or out of a system? So first of all, let's just review gas, liquid, and solid, right? The changes of phase. Changing from one phase to another is only a physical change. As a reminder, it is not a chemical change. But even those processes will absorb or release energy. So again, we've talked a lot about the fact that chemical reactions absorb and release energy. It's also important to recognize that physical changes also can absorb and release energy. So here we go. We've got our ice cubes. You know that in order for those to melt, it has to take energy in. It is endothermic, so adding energy will melt the ice into liquid water. And you also know that this liquid water, if I want to change it back into a solid, it has to release heat in order for it to freeze. So removing energy will freeze the liquid water into ice. This is a very important document. All right, so it says phase changes between the most common phases, know these. So taking a look at this, if we are in the solid and we want to go to a liquid, well, first of all, a solid changing into a liquid, most of you would tell me melting. But what's going on with this arrow? Does that have something to do? Well, what did we just talk about in the last thing? In order for ice to melt, what has to happen to the energy? Hopefully you said that the ice, the solid, has to absorb energy, all right? And then if we have the liquid and we want to turn it into a gas, well, what has to happen with energy there, right? And certainly that process of changing a liquid to a gas is called vaporization. So again, notice the color here. Is there anything there with color? In going from a solid directly into the gas. Now, this is probably one that you're not terribly familiar with. It's called sublimation. So can a solid go straight into a vapor? Absolutely. If you've ever had ice cubes in your freezer for a really long time and you've opened up your freezer and a fog came out on a really hot day, you have experienced sublimation, right? And your ice cubes get all deformed. Yeah, sublimation. Anyway, in order for us to go from a solid to a gas directly, am I absorbing heat? Am I releasing heat? So hopefully you understand. Red means endothermic because these processes are absorbing energy. Now let's take a look at the green ones, right? So if I'm going from a gas back into a liquid, that's called condensation. Now, gas, high energy state, in order for it to condense, it has to lose heat. That means it is exothermic. So the process of going from a gas to a liquid, exothermic. The process of going from a liquid to a solid, called freezing. And again, you have to give off heat. It is exothermic. And the process of going straight from a gas to a solid, again, another one you're probably not terribly familiar with. Gas going directly to a solid is called deposition. And again, also exothermic. So green lines mean that process gives off heat. Red line means that process is endothermic and requires heat. So make sure you know these. All right, temperature remains constant while a substance is transitioning from one phase to another. Now, this is a diagram for water, particularly. I'm going to grab sorry about that. Okay, here is 0 degrees Celsius. Here is 100 degrees Celsius. So we are looking at right there, and we are looking at right here. And notice the change of my circles. Like the circle here is much smaller than the circle here. What does that mean? Well, down here at the bottom, our x-axis, as we move in this direction, heat is continuing to be added. As we go here, temperature is rising, right? So we can see here we are at freezing or melting. By the way, freezing in one direction, melting in the other. So what's the freezing temperature of water? 0 degrees Celsius. What's the melting temperature of water? I hope you said 0 degrees Celsius, right? Here, boiling. What's the temperature of water boiling in degrees Celsius? It's 100 degrees Celsius. What is the condensation temperature of water? 100 degrees Celsius. But as I'm coming back here, we can see that yes, heat is continuing to be added while this phase change is happening. But the graph is not continuing to go up. It is going straight. Temperature is not changing during the phase of going from a solid to a liquid. As a matter of fact, this is a combination of both ice and liquid at the same time. So that is not going to change until all of the ice has finally melted. Once it finally melts, then as the heat continues to be added, now we're going to see the temperature start to rise until we get to 100 degrees Celsius. And then suddenly we see it go straight again. Static, right? The line stops changing. What's going on? Water's boiling. And when water's boiling, and you've seen this happen, you can test this for yourself, you have a combination of both liquid water and steam, right? And you're going to continue to add energy. Energy is continuing to be added, but the temperature of the liquid is not changing until all of that water changes from a liquid to a vapor. And then if we continue to add energy, then the temperature of that water is going to rise again. All right, so this is called a heating cooling curve for water. So as you look right here from 20 to 0, what is the phase? This is ice. And when the line is not changing, that's a phase change, right? That's melting or freezing. So if I'm going this way, it's freezing. If I'm going this way, it's melting, all right? Here, from here to here, this is liquid water. And again, straight, this is a phase change. We have in this direction, it would be boiling. In the opposite direction, it would be condensation. And then up here in the red line, we are now pure steam, okay? So just a little explanation on that little graph there. Oh, so sad. If we were together, I promise you. Mr. Holguin has a blowtorch. He definitely does this. Me, I keep asking for a blowtorch for Christmas. Well, actually, that's not true. I forget. But I want to get a blowtorch. Fun experiment. Okay, calculating the energy required for state changes of state. The heat of fusion. So we can actually calculate how much energy is absorbed or released for different substances. So every substance is going to have its own unique amount of energy that is required in order to melt it or freeze it. So heat of fusion is the energy required to melt a substance. This happens to be water. And water at 0 degrees Celsius is going to take us 334 joules of energy per gram of water. So that's a relationship. So 1 gram of water, 334 joules of energy. Now, in one direction, that is water that is being absorbed. So we are, one direction, that's water that's being absorbed. So that's energy that's taken in. And the other direction, it would be the same amount of energy being released. So melting or freezing. All right, heat of vaporization is the energy required to convert a substance to vapor. So again, we are at the boiling point. We're at 100 degrees Celsius. So again, these are phase changes. We're going to use these during phase changes. We're going to use this one for melting and freezing. We're going to use this one for boiling and vaporization. All right, now you'll see, look at for water. It takes 2,260 joules for every 1 gram of water. So it takes more energy to boil water than it does to melt it. That's a fun question. Okay. Reminder, temperature remains constant during a phase change. So constant on our graph means that the line stays straight. All right, so we've been talking about these phase changes, and it's important to note that again, first year students oftentimes want to use our equation for energy, Q equals M times C times delta T. And let's talk about why we can't use this. We cannot use this during a phase change. Just as a reminder, Q equals energy, right? M equals mass. It doesn't really matter what the numbers is. C equals specific heat, right? And delta T is a change in temperature. Let's see, change in temp. All right, but remember, the line is straight. Let me go back to our graph here on the previous slide, right? If we're here, this line is straight. Is temperature changing? So what would be my value for delta T? Well, my value for delta T is going to be 0 because there's no change, right? And 0 times anything else is going to equal 0 energy. So is there 0 energy during melting? No. So this would be a reason that you cannot use Q equals M times C times delta T during any phase change. You can use Q equals M times C times delta T if you're moving from here to here, or you're moving from here to here. Yes, because there's a temperature change and you will have a change in energy. Okay, all right, let's go on. Okay, so here's our first problem. How many joules of energy are required to melt 8.5 grams of water ice at 0 degrees Celsius? All right, the biggest thing that you have to do with these problems is really figure out the information, right? What is it asking of me? Well, first of all, it's asking for how many joules, and joules is energy, are required to melt. Melting is a phase change, right? So that means I am right here, right? And I have a combination of ice and water. And it's telling me that I have 8.5 grams of that ice-water mixture. So what I need in order to do this is the heat of fusion of water, which we have here. So the heat of fusion for water is 334 joules per gram. So now I'm going to come back over here. Whenever we do a problem like this, we always start with what's given. So here's our 8.5 grams of water. Now we're going to use that relationship between grams and joules. So if this is grams, then I want to make sure, and I'm going to just do this here. Let's get back to this. Grams is going to go downstairs. Joules is going to go upstairs, right? And so I'm going to put in my 8.5 grams. No, I'm sorry. I'm going to use my heat of fusion. My 1 gram and 334 joules. Okay, now I'm going to erase this because I have it all pretty on the slide. So there you go. And now we can see that our grams of water cancels and we're left in joules, which is what we're looking for. That's what tells us it's time to do our calculation. So we grab our calculators and we find that we have 2,800 joules of energy added. But don't forget, we have to put that in scientific notation. So 2.8 times 10 to the third joules of energy. All right, we're working on example problem 9.7. So how much ice in grams can you melt at 0 degrees Celsius with 953.67 joules of energy? So, again, I've got 953.67 joules. Joules is energy. And the question is, how much ice? Well, and it does tell me in grams. So I'm going to put question mark, grams of H2O. All right, so I have been given 953.67. The question is, how many grams of water can we melt with this ice? So again, you need that heat of fusion. So you have the heat of fusion for water, which is 334 joules per gram, per 1 gram. So we're going to use those two things. So again, by extracting that information and stripping away all that language, I think it makes it a little more clear. We always start with what's given. So I'm going to go ahead and erase this because I have it written in the PowerPoint nice and pretty. So you start with what's given, that's your joules, and we're going to use our heat of fusion. You can see we've got joules and joules canceled. Now we've got grams of water. This is what signals. What am I looking for again? Grams of water. Yes, that's what tells me. I grab my calculator and I come up with my answer, 2.86 grams of water. And again, these are problems that you'll see on your homework. All right, example problem 9-8. How much water in grams can you vaporize at 100 degrees Celsius with 953.67 joules? Now, this problem looks very much like the last problem, except we are vaporizing the water. We are not melting or freezing the water. So we have a different, we're going to use the heat of, not fusion, it's heat of sublimation, vaporization, yeah, heat of vaporization. All right, so again, I'd recommend pull out this information. So we have 953.67 joules. And what do I want to know? I want to know how many grams of H2O. Since I am vaporizing, I need the heat of vaporization. So the delta H of VAP, right? And I believe it's 2,206 joules per every 1 gram, right? That gives me a relationship. So I've got joules, I want to go to grams, I can use this to get there. Now I'm going to erase this because it's nice and pretty on the PowerPoint already. Starting with, you always start with what's given. And again, here we're going to put joules downstairs, we're going to put grams upstairs because we want the joules to cancel. And we want grams of H2O up here. And then I can look at my relationship and put my joules downstairs and my grams upstairs. And let me erase that. And we have 0.422. Again, do not forget, always box out your answers, right? Little hints as we go along the way. Okay. Again, some more problems you'll actually be working on that are just like this. So remember that the problems that we do in this PowerPoint are models for you to follow, right? So as you run across similar situations, you can look at these problems to help you. All right, here is the mother of all problems, right, for this unit. So example problem 9-9, how many joules of energy are needed to convert 25 grams of ice at minus 25 degrees Celsius entirely to vapor at 125. So ladies and gentlemen, we're not even on this graph. We're here, minus 25 degrees Celsius, all the way up here to 125 degrees Celsius. So what do we have to do? Well, we've got to heat the ice up. So that means that's a temperature change, going from minus 25 to 0, right? So we have to go from minus 25 degrees Celsius to 0. That is a Q equals M times C times delta T, right? At 0, well, and let's go, now we got to go, well, I like to go all the way, right? Step by step. So once we get to 0, then we've got a straight line. That means you've got to use the heat of fusion. Right? Heat of fusion at 0 degrees Celsius, right? By the way, this is degrees Celsius. All right? Once you figure out how much energy it's going to require to melt the H2O, right? So this is going to tell you how much energy is required to heat it up to 0. This is going to tell you how much energy is required to melt it to liquid water. Then we're going to go from 0 degrees Celsius to 100 degrees Celsius. So if I'm here at 0, I have a temperature change. So I'm going to use Q equals M times C times delta T again. So I can figure out how much energy is it going to require to heat all of that water, 25 grams, all the way to 100 degrees Celsius. And then I have another phase change. So I'm going to use the delta heat of vaporization at 100 degrees Celsius, right? And that's going to be the amount of energy to vaporize all of that H2O. And then once I vaporize all of the H2O, we're going to go from 100 degrees Celsius to 125 degrees Celsius using Q equals M times C times delta T. All right. That's just think the problem out. Here we go. Oh, let me get rid of this here. So now here we go. We're going to write it all out. Calculate the energy for each phase change. So, is there a specific order of operations that you have to do? No. But we have 2 phase changes. So, could you go ahead and just calculate the phase changes first? Absolutely. Calculate the energy for each change in temperature. We have a change in temperature here, we have a change in temperature here, and we have a change in temperature there. Right? So we have 3 areas where we have a change in temperature. And then we're going to add all of those energies up to get the total energy to take it from minus 25 all the way to 125. Now, here are all of the things that you're going to need. You're going to need the heat of vaporization and the heat of fusion for your phase changes. You're going to need the specific heat of water. And water has a different specific heat for each of its phases. So this would be the specific heat for water as ice, the specific heat for water as liquid, the specific heat for water as a gas. The energy to raise the ice from minus 25 to 0. So we talked about that. So we're going to use Q equals M times C times delta T. We have been given the fact that the total mass of water that we're dealing with is 25 grams. So anytime I need mass in these equations, it's going to be 25 grams. Using the specific heat of ice, so coming here, 2.11 joules per gram, and the delta T going from 0 to 25 degrees Celsius, or from minus 25 to 0 is a 25 degree change, okay? So that gives us a very big number, no rounding. All right, the energy to melt the ice, like we talked about, that's a phase change. So we have our 25 grams. We're going to use the heat of fusion, which is 300, for every 1 gram, there's 334 joules, and we have 8,350. No rounding. All right. The energy to raise the water from 0 to 100. So what equation are we going to use for that? All right, hopefully you say Q equals M times C times delta T. We have the M, 25. The C, we have to make sure this is liquid water, so it's going to be 4.184 joules per gram. And we're going to have 100 degrees of change going from 0 to 100. And again, 10,460 joules. The energy to vaporize the water. So here we are, vaporize is a phase change. We have a straight line. We're going to use the molar heat of vaporization. So starting with our grams, 2,260 joules. We have 56,500 joules to vaporize the water. All right, we have one more equation to do, and then we can add these all up together. So the energy to raise the temperature of the water vapor from 100 to 125. So we're going to use Q equals M times C times delta T, 25 grams, different specific heat, right? Because now it's a vapor, so it's going to be 2 grams, or 2 joules per gram times degrees Celsius. And temperature change from 100 to 125 would be 25 degrees of change, 1,250 joules. So for the total energy, we're going to add all those up. All right, so here we go. Now we're going to add up all of those energies. All right, and again, we want to line them up in a way to help us, use the rule for adding measurements, right? So when we do this and we add it up this way, sometimes it helps to make it a little bit easier to see where we're supposed to round it. So we add them all up. Can you see where we're supposed to round it? All right, hopefully you saw that in 56,500, these are both not significant zeros. So we're going to be rounding at this hundreds place. So we're going to look at that 8. 7's going to change that to a 9. So it's going to be 77,900 joules of energy required, correctly rounded. And of course, do we leave it like that? we need to put it in scientific notation. So 7.79 times 10 to the 4th joules. All right, good luck with working on these problems. Be patient and seek help if you need it.